cellular networks. The overall service area divided into small cell, ideally with no gaps or overlaps, each cell being served by its own base station and a set of channel frequencies. The power transmitted by each station is controlled in such a way that the local mobile stations in the cell are served while co-channel interference in the cells using the same set of radio channel frequencies is kept minimum. The factors affecting number of channels in a particular area is first option. The first one is the available frequency spectrum, the cell size or transmitter power, the reduction in the quality of the link that can be tolerated due to the co-channel interference. The normal maximum number of channels operating in a cell is limited to 120, and this occurs in places where the traffic is highest. The capacity of system in an area is determined by the number of channels in a cell and the cell size. Cellular network organization. Each cell is allocated a band of frequencies and is served by a base station consisting of transmitter, receiver and control unit. Adjacent cells are assigned different frequencies to avoid interference or crosstalk. However, cells sufficiently distant from each other can use the same frequency band. A hexagonal pattern provides for free equidistant antennas as shown in figure below. There can be other geometries like circular geometry also, but there will be some area left out with circular geometry. Frequency reuse. The frequency reuse concept is instead the objective is to use the same frequency band in multiple cells at some distance from one another. This allows the same frequency band to be used for multiple simultaneous conversions in different cells. Moreover, within a given cell, multiple frequency bands are assigned and number of bands depends on traffic expected. A key design issue is to determine the minimum separation between two cells using the same frequency band so that the two cells do not interfere with each other. Various patterns of frequency reuse are possible. Figure below shows some examples for different values of I, j. The pattern consists of n cells and each cell is assigned the same number of frequencies. Each cell can have k by n frequencies, where k is the total number of frequencies allotted chosen to the system. In hexagonal cells, patterns only the following of n's are possible. Capital N equal to I square plus j square plus I into j, where I, j equal 0, 1, 2, 3 and so on. Hence the possible values of n are 1, 3, 4, 7, 9, 12, 13, 16, 19, 21 and so on. On the following relations holds good. D by R equal to root over 3n. 3n full root of this can also be expressed as capital D by small d equal to root n, where capital D is minimum distance between centers of cells that use the same frequency band called co-channels. Capital R means radius of a cell, small d means distance between centers of adjacent cells, small d equal to 1.7 R, capital N equal to reuse factor R, cluster size. Hard handoff. A hard handoff is essentially a break before no make connection. In hard handoff, the link to the prior base station is terminated before or as the user is transferred to the new cell's base station. This means that the mobile station is linked to no more than one base station at a given time. Under the control of the mobile switching center MSC, the BS hands off the MS call to another cell and then drop the call. Soft handoff or handover is a mobile cellular network technology commonly used in CDMA, code division multiple access systems, that enables the overlapping of the repeater coverage zones so that every mobile station is always well within a range of at least one of the base stations. A soft handoff mechanism works by first switching and establishing connection with another base station before disconnecting from the existing base station in the network. So it is also sometimes referred to as make before break handoff. The soft handoff technology has many advantages, like since there is no change in frequency or timing as the mobile set passes from one base station to another base station, so there are practically no dead zones. Therefore, the connections face negligible interruption and dead zones are practically non-existent. Co-channel interference. with frequency reuse, many cells at a distance will be using the same frequency bands within a given area. These cells are called as the co-channel. There is a possibility of interference between them since they are operating at same frequency. The interference between them is called as co-channel interference. For a 7-cell cluster, there could be up to 6 immediate interference. The co-channel interference is a function of a parameter Q, capital Q equal to capital D by capital R. The parameter capital Q is called the co-channel interference reduction factor. Factor capital Q is independent of actual power level P0, which is assumed to be same for all cells. Reuse factor D by R, capital D by capital R equal to root 3n, root over 3n. So R by D equal to 1 by root 3n, that equal to 3n whole power minus 1 by 2. C by I equal to 1.5 n square, where C by I ratio is a function of cluster size. Next, adjacent channel interference, ACI. Adjacent channel interference occurs from channels in adjacent neighboring cells. This is worst in small cell clusters. Adjacent channel interference results from imperfect filters in receivers that allow nearby frequencies enter the mobile unit. It can be observed when an adjacent channel is transmitting and the mobile unit is receiving at an adjacent frequency. This is called a near-far effect. Adjacent channel interference can be reduced by designing precise filtering receivers and assigning frequency channels. The best thing one can do is to keep adjacent channels as far apart. Optical communication block diagram. General mode of an optical communication system is as information source, transducer input, information source, next output source, optical source, next optical channel, next optical detector, next electrical receiver, next destination. Transducer basically converts information from source into electrical source. Optical source, laser or LED, converts electrical signal into optical light signal. Optical channel is optical filter. Optical detector converts optical signal into electrical signal. Mainly avalanche photodiode is used. Avalanche photodiode is used. When you have to compare the behavior of light in two medium, that we go for ray theory. When we deal with transmission of optical signal or reception of optical signal, then we go for wave theory. If there is an interaction between a material and light, then we go for photon theory. Then we go for photon theory. Refractive index N. Refractive index is defined as the ratio of velocity of light in free space to velocity of light in medium, for which we are calculating refractive index, that is N equal to C by V. Value of refractive index is always greater than or equal to 1. Total internal reflection by Snell's law, N1 sin phi 1 equal to N2 sin phi 2. If phi 2 equal to 90 degrees, internal reflection takes place. Phi 1 equal to sin inverse of N2 by N1. N1 greater than N2. Total internal reflection will take place if the angle of incidence phi 1 is greater than or equal to critical angle phi c, that equal to sin inverse of N2 by N1. All the information in optical fiber is carried by the principle of total internal reflection, and all the information is carried in core of optical fiber. Cladding does not support any transmission of information. Acceptance angle, when N1 and N2 refractive indices of core and cladding respectively, acceptance angle is the maximum angle of the to the fiber at axis at which the light may enter in order to propagate through the fiber. If angle of incidence to the fiber is greater than theta A, then total internal reflection will not take place in optical fiber and information will be lost. Numerical aperture, it is the measure of light accepting collecting ability of fiber. It establishes the relationship between acceptance angles and refractive indices of a different medium involved. Na equal to sin theta A equal to root over n1 square minus n2 square. Refractive index, relative refractive index difference delta, it is defined as delta equal to n1 square minus n2 square by 2 n1 square. Delta is approximately equal to 1 minus n2 by n1. Numerical aperture equal to n1 into 2 delta whole power 1 by 2. 2 delta మాత్రమే 1 by 2 వస్తుంది whole power. n1 పక్కన multiplication factor. Meridian and skew rays. Meridional rays are those rays which pass through core axis. Skew rays are those rays which do not pass through core axis. Numerical aperture for meridian and skew rays. For meridian rays, numerical aperture is Na equal to sin theta A equal to n1 square minus n2 square under root full. For skew rays, numerical aperture is Na equal to sin theta As cos gamma, that equal to n1 square minus n2 square whole power 1 by 2 into cos gamma. Into అనేది పక్కన వస్తుంది, సెపరేట్ cos gamma వేరు. theta A is acceptance angle for skew rays. Gamma is the angle between angle of incidence and normal at the point of incidence. Theta A is always greater than theta A. Skew rays will be in large number inside fiber. Normal frequency V number, it is a dimensionless quantity and is given by V equal to 2 pi by lambda into 2 pi by lambda is a factor into A into NA. 2 pi by lambda into A into N1 into 2 delta whole power 1 by 2. 2 delta మాత్రమే 1 by 2 వస్తుంది. where A means core radius, lambda means wavelength of operation. Step index fiber N of R equal to N1 for R less than A equal to N2 for R greater than A equal to A. The refractive index profile for this type of fiber makes a step change at the core cladding interference. The core cladding interference. Graded index fiber has variable refractive index inside core. Refractive index is maximum at the center of core and decreases as radial distance increases from the core. This type of profile for refractive index is used for propagation of multimode with equal delays. Refractive index profile is N of R equal to N1 into full into 1 minus 2 delta R by A whole power gamma whole power 1 by 2. N1 పక్కన పెట్టేసి రూట్ ఓవర్ అని వచ్చేసి 1 పక్కన మైనస్ 2 డెల్టా పక్కన ఆర్ బై ఏ హోల్ పవర్ ఆల్ఫా. ఆర్ బై ఏ మాత్రమే పవర్లో ఆల్ఫా వస్తుంది. దానికి N1 కాకుండా మిగతా 1 by 2 వస్తుంది. అది దాని రూట్ ఆర్ లెస్ దాన్ ఏ. N2 ఈక్వల్ టు N1 ఇంటూ 1 మైనస్ 2 డెల్టా పవర్ 1 by 2. 1 minus 2 డెల్టాకి మాత్రమే పవర్లో 1 by 2 వస్తుంది. where alpha is profile of the fiber. Value of alpha profile value of alpha infinite అయితే step index. Value of alpha 1 అయితే profile triangular. Value of alpha 2 అయితే profile parabola. As the alpha increases, graded index fiber will tend towards steps index fiber behavior. Modes are equal energy and equal phase. Same phase but unequal energy. Different phase but same energy. Number of modes are mode volume m equal to v square by 2 for step index. Number of modes are mode volume mg is given by mg equal to alpha by alpha plus 2. Alpha కు మాత్రమే alpha న్యూమరేటర్ పార్ట్ alpha plus 2 అనేది డినామినేటర్. అది alpha into v square అనేది న్యూమరేటర్ పార్ట్ alpha plus into 2 అనేది డినామినేటర్ for graded index fiber. Due to multimode transmissions, different waves reach destination at different time. This multimode transmission is known as dispersion. If you reduce the radius such that single mode is only transmitted through core, so no dispersion and so no different delays. If you want to transmit only single mode, then normalized frequency must be in the range 0 less than or equal to V less than or equal to Vc, where Vc equal to 2.405. For single mode transmission, minimum value of wavelength lambda is given by lambda minimum equal to 2 pi a into numerical aperture whole by 2.405. Losses in optical fiber. Absorption losses intrinsic due to interaction of one or more major components of glass. Extrinsic due to OH minus ions or due to transition element impurity. Linear scattering losses. First one Rayleigh loss, second one MIE loss. To non-linear scattering losses, fiber band losses. Optical sources. Normally used optical sources are laser and LED. Laser is the source of monochromatic and coherent light. LED is the source of monochromatic and non-coherent light. In case of helium neon laser, for same output of optical power, less input power is required as compared to ruby laser. In case of LED, total recombination rate RT is directly proportional to forward biased current and is given by RT equal to RNR plus RR, where RNR means non-radiative recombination, RR means radiative recombination. Relation between the overall mean lifetime tau 1, mean lifetime tau r corresponding to radiative recombination, and mean lifetime tau n r corresponding to non-radiative recombination is 1 by tau t equal to 1 by tau r plus 1 by tau n r, and NINT equal to RR by RT equal to tau t by tau r. Optical detector used is normally avalanche photodiode or pin diode. Optical detector must have high sensitivity, high fidelity, short response time and stability within the range of operation. Quantum efficiency of optical detector. Quantum efficiency of optical detector is given by eta d equal to electron generation rate by incident photon rate, that equal to RE by RP, where RE and RP are electron and photon generation rate respectively. Responsivity capital R, it is given the transfer characteristics of the detector and is equal to capital R equal to IP by P naught, where IP means photocurrent, P naught means photo instant photon power, P naught equal photon rate, RP into HF, RE equal to eta P naught by HF. Now R equal to IP by P naught equal to ERE by P naught equal to eta DE by HF, where IP equal to ERE. There is always a trade-off between speed of operation and sensitivity of detector. Propagations of waves. In Earth environment, electromagnetic waves propagate in ways that depend not only on their own properties but also on those of environment itself. Frequency ranges of wave propagation are ground wave propagation less than 2 MHz, sky wave or atmospheric wave propagation 2 MHz to 30 MHz, space wave propagation per loss equal to 30 MHz. Ground wave propagation. Ground wave propagates along the surface of Earth. Ground waves are vertically polarized to prevent short circuiting of electric component. These are also called surface waves. Ground waves are used up to medium frequency range. AM is an example of ground wave propagation. Field strength at a distance for ground wave. The field strength in volts per meter is given by taking into account the gain of transmitting antenna, capital E equal to 120 by HTI by lambda D. If your receiving antenna is now placed at this point, the received signal will be V equal to 120 by HT by lambda D. 120 pi means characteristic impedance of free space, HT means effective height of transmitting antenna, HR means effective height of receiving antenna, I means antenna current, D means distance from the transmitting antenna, lambda means wavelength. The distance between the two antennas is fairly long. The reduction of field strength due to ground and atmospheric absorption reduces the values of the voltage received. At low frequencies, absorption is less due to ground, so wave propagation can take place for a large distance. Sky wave. Ionization of the upper parts of Earth's atmosphere plays a part in the propagation of radio waves, particularly at high frequencies. There are several layers of ionization which under certain conditions reflects back to Earth the high frequency waves that would otherwise escape into space. Ionosphere is the upper portion of the atmosphere which absorbs large quantities of radiant energy from the sun, becoming heated and ionized. D layer is the lowest, then E layer, then ES layer, then F1 layer, and in last F2 layer. Reflection occurs from ionization layers due to bending of waves. It travels through different layers. This figure shows that as a wave is refracted, it went down gradually rather than sharply. However, below ionized layer, the incident and refracted rays follow paths that are exactly the same as they could have if reflection had taken place from a surface located at a greater height, called virtual height. Critical frequency Fc. Critical frequency Fc for a given layer is the highest frequency that will be returned down to Earth by that layer after being beamed straight up at it. Critical frequency range for F2 layer is from 5 MHz to 12 MHz. Maximum usable frequency MUF. Maximum usable frequency is a limiting frequency but for some specific angle of incidence other than the normal, and it is given by MUF equal critical frequency by cos theta, MUF equal to FC secant theta. Normal values of MUF may range from 8 to 35 MHz. Above equation is also called secant law. Skip distance is the shortest distance from a transmitter measured along the surface of Earth at which a sky wave frequency less than Fc will be returned to Earth. A frequency which makes a given distance corresponds to the skip distance is the MUF for that pair of points. Transmission point is limited by the skip distance at one end, the curvature of the Earth at the other end. Fading is the fluctuation in signal strength at a receiver and may be rapid or slow, general or frequency selective. Fading can occur because of interference between the lower and upper rays of sky waves. AM signal suffers from frequency selective fading. Space waves. Space waves travels are more or less in straight lines. Space waves are limited in their propagation by curvature of the Earth. Radio horizon. The radio horizon for space waves is about 4/3 as far as optical horizon. The radio horizon of an antenna is given by dt equal to 4.12 into root ht plus root hr kilometers, where dt means distance from transmitting antenna, ht means height of transmitting antenna above ground in meters. The optical horizon of an antenna is given by dt equal to 3.57 into root ht plus root hr kilometers. Note by default, radio origin is considered line of sight LOS propagation. This is also called Frisk transmission. PT is power transmitted by antenna and PR is power received by receiving antenna. GT, GR are gains of transmitter and receiver respectively. Then received power is given by PR equal to PT GT into AE by 4 pi d square. PR equal to PT GT into AE by 4 pi d square, where D means direct distance between two antennas, AE means effective area of receiver, GR equal to 4 pi AE by lambda square. GR equal to 4 pi AE by lambda square. So received power PR equal to PT GT GR whole by 4 pi d by lambda whole square. 4 pi d by lambda మాత్రమే స్క్వేర్ వస్తుంది. సో రిసీవ్డ్ పవర్ in dB is 10 log 10 PR equal to 10 log 10 PT plus 10 log 10 GT plus 10 log 10 GR minus 20 log 10 4 pi d by lambda. Term 20 log 4 pi d by lambda corresponds to path loss. Satellite communication. Satellite communication systems exist because Earth is a sphere. A repeater is needed to convey signal over long distances. A repeater is simply a receiver linked to a transmitter. Satellite system operates in the microwave and millimeter wave frequency bands. Uses frequency between 1 and 50 GHz. There are 4 satellite systems whose orbital velocity, height and period is given as satellite system. Intelsat Geo, orbital height 35786.03, orbital velocity 3.0747 km per second, orbital period 23 hours 56 minutes 4.1 seconds. New ICO MEO, orbital height 10255, orbital velocity 4.8954 km per second, orbital period 5 hours 55 minutes 48.4 seconds. Skybridge LUO, orbital height 1469, orbital velocity 7.1272 km per second, orbital period 1 hour 55 minutes 17.8 seconds. Iridium, orbital height 780, orbital velocity 4.4624, orbital period 1 hour 40 minutes 27.0 seconds. Time period. Satellite orbit is given by T equal to 2 pi r power 3 by 2 whole by mu power 1 by 2, where r means distance of satellites or orbit from the center of Earth, mu means constant which is product of gravitation constant G, and mass of Earth me. Kepler gives the relation between orbital period and semi-major axis of elliptical path, and is T square equal 4 pi square a cube by mu. T square equal 4 pi a square a cube by mu, where a means semi-major axis of ellipse and replaced by r if path is circular. Mu means Kepler constant. ఇటు సైడ్ మ్యాక్సిమం అంటే అపాజీ, ఇటు సైడ్ అంటే పెరిగి. అపాజీ అంటే ఏ ఇంటూ 1 ప్లస్ సి, పెరిగి అంటే ఏ ఇంటూ 1 మైనస్ సి, మధ్యలో ఏఈ వస్తుంది. అపాజీకి సెంటర్ ఆఫ్ పాయింట్కి ఏ వస్తుంది. మేజర్ యాక్సిస్, మైనర్ యాక్సిస్ ఏమో బి వస్తుంది. ఓకేనా. సెమీ మేజర్ యాక్సిస్ అండ్ మైనర్ యాక్సిస్ లెన్స్ ఆర్ గివెన్ బై స్మాల్ ఏ ఈక్వల్ టు పీ బై 1 మైనస్ ఈ స్క్వేర్, వేర్ బి ఈక్వల్ టు ఏ బై రూట్ డినామినేటర్ అంతా root 1 minus c square. Denominator part is root 1 minus c square, where p means semilateral spectrum of ellipse, e means eccentricity of ellipse. Geostationary and geosynchronous satellites. Geostationary satellite is in geostationary and geosynchronous satellites. Geostationary and geosynchronous satellites. Geostationary satellite is in a orbit whose period is same as that of Earth's rotation period. It remains stationary with respect to any point on Earth at any time. Geosynchronous satellite will be at fixed position with respect to a point on Earth at the same time every day, but not all the time. Geostationary satellite has circular orbit E equal to 0 and has 0 inclination with respect to equator. Geosynchronous satellite has an inclination with respect to equator, and also its orbit is not circular. The average angular velocity of satellite is given by eta equal to mu power 1 by 2 by a power 3 by 2, that equal to 2 pi by t, where eta means average angular velocity. Satellite link design. Major bands used for satellite communications are 6 bar 4 GHz, 14 bar 11 GHz, 30 bar 20 GHz. The uplink frequency is written first by convention. As frequency increases, attenuation in atmosphere increases. All communication links are designed to meet certain performances using a bit error rate BER. In a digital link or a signal to noise ratio S/N in an analog link, the baseband channel BER or S/N ratio is determined by the carrier to noise ratio C/N and the input to the demodulator in receiver. In most satellite communications applications, the C by N ratio at the demodulator input must be greater than 6 dB. Overall C by N at that station receiver depends on both uplink and downlink. If a transmitting source in free space radiating a total power PT watts uniformly in all directions and GT is gain of the antenna, then PT/GT is called electric isotropically radiated power EIRP. Now received power by an antenna at a distance r from the transmitter having gain GR is PR equal to PT/GT GR whole by 4 pi r by lambda whole square. 4 pi r by lambda whole square మాత్రమే whole square వస్తుంది. PR equal to EIRP into receiving antenna gain by path loss watts in decibel. Received power will be PR dB equal to EIRP dB plus GR dB minus LP dB, where LP dB equal to path loss in dB. LP dB equal to 20 log base 10 into 4 pi capital R by lambda. In general, received power is given by PR dB equal to EIRP dB plus GR dB minus LP dB minus LA dB minus LTA dB minus LRA dB, where LA dB is loss in dB in atmosphere, LTA dB means loss associated with transmitted in dB, LRA dB means loss associated with receiver in dB. System noise temperature. At microwave frequencies, a black body with a physical temperature Tp degrees Kelvin generates electrical noise power in a wide bandwidth. The noise power is given by Pn equal to Kp Tp Bn, where K means Boltzmann constant, Tp means physical temperature of source in Kelvin degree, Bn means noise bandwidth in which noise power is measured in Hz. Ktp is noise power spectral density in watts per Hz. The power spectral density in constant for all the radio frequencies up to 300 GHz. To determine the performance of a receiving system, we need to be able to find the total thermal noise power against which the signal must be demodulated. This is done by determining system noise temperature. System noise temperature TS is the noise temperature of a noise source located at input of noiseless receiver, which gives the same noise power as the original receiver measured at the output of the receiver and usually includes noise from the antenna. If the overall end-to-end gain of receiver is GRX and his narrowest bandwidth is PNH, the noise power at the demodulator input is given by PN0 equal to KTS BN GRX. TS means system noise temperature, PN0 means noise power at a demodulator input, GRX means gain of receiver from RF input to demodulator input. The noise power referred to the input of receiver is PN, where PN equal KTS BN. If antenna delivers a signal power PR to the receiver RF input, then carrier to noise ratio at the demodulator is given by C by N equal to PR by whole by KTS BN. System noise temperature TS is given by TS equal to Tin plus TRF plus Tn by GRF plus TAF by GF, where Tn equal to noise temperature of the antenna measured at its output port. TRF means equal to noise temperature of RF amplifier. TAF means equal to noise temperature of IF mixer. TM means equal to noise temperature of mixer. GRF means gain of RF amplifier. GM means gain of mixer. GIF means gain of IF amplifier. Succeeding stages of receivers contribute less and less noise to the total noise temperature. In this case, system noise temperature is simply the sum of antenna noise temperature and LNA, low noise amplifier noise temperature, that is TS equal to T antenna plus T LNA, where T antenna equal to noise temperature of antenna, T LNA means noise temperature of LNA. Noise model for an equivalent output noise source produces a noise temperature Tn0 given by Tn0 equal Tp into bracket లో 1 minus G1. 1 minus G1 అనేది bracket లో ఉంటుంది, Tp into 1 minus G1, where G1 means linear gain less than unity of attenuating devices of medium. Tp means physical temperature of device or medium in Kelvin degrees. Noise figure and noise temperature. Noise figure is frequently used to specify the noise generated within the device. The operation noise figure NF is defined as the ratio of signal to noise ratio at the input to the signal to noise ratio to the output of a device and is given by noise figure equal to signal to noise ratio of input by signal to noise ratio of output. Noise figure in terms of equal noise temperature NF equal to 1 plus T0 by T0. 1 separate, T0 by T0 separate. T0 means equal noise temperature, T0 means reference temperature and is 290 K. If several devices are cascaded, then overall noise figure can be found using Friis formula as F equal to F1 separate plus F2 minus 1 numerator part by G1 denominator part plus F3 minus 1 numerator part G1 G2 denominator part plus F4 minus 1 numerator part G1 G2 G3 denominator part, Fn minus 1 numerator part G1 G2 G3 and so on, Gn minus 1, where F1 F2 F3 and so on F1 are respective noise figure of devices in cascade. G1 G2 G3 and Gn are respect to gains of device in cascade. Precautions must be taken while using above formula. G1, G2, Gn must be numbers, should not be in dB. G by T ratio of earth station, the ratio of receiver gain Gr to system noise ratio temperature Ts. The link equation can be written in terms of C by N at earth station. C by N equal to numerator part Pt Gt Gr, denominator part K Ts Bn into lambda by 4 pi r whole square. Lambda by 4 pi r కి హోల్ స్క్వేర్ వస్తుంది. దాని పక్కనే ఈ రెండు బ్రాకెట్లో వచ్చి దాని పక్కనే ఇంకో బ్రాకెట్లో వచ్చి lambda 4 pi r హోల్ స్క్వేర్ వస్తుంది. దట్ ఈస్ నథింగ్ బట్ Pt Gt by Kbn into lambda by 4 pi r square into Gr by Ts. So higher the G by T ratio, the higher will be CBN ratio and better will be reception of signal at receiver. So G by T ratio is figure of merit for receiver. Sometimes it is given that satellite terminal has negative G by T, which means it is below 0 dB per Kelvin, means numerical value of Gr is smaller than numerical value of Ts. Link budget. A link budget is a tabular method for evaluating the received power and noise power in a radio link. Link budget is invariably used in decibel units. Relation between uplink attenuation and downlink attenuation is given by A up equal to A down into FUP by F down whole square. FUP by F down మాత్రమే స్క్వేర్ వస్తుంది, మిగతా దానికి రాదు. A down is separate, so A down into FUP by F down whole square. AUP means uplink attenuation in atmosphere mainly due to rain. A down means downlink attenuation in atmosphere mainly due to rain. F up, F down means uplink and downlink frequencies respectively. Relationship between overall CBN ratio and CBN for uplink and CBN for downlink as 1 by CBN overall equal to 1 numerator loss of the CBN up plus 1 numerator loss of the CBN down. CBN overall equal to overall CBN to ratio. CBN up means CBN ratio for uplink, CBN down means CBN ratio for downlink. That is about the advanced communications.